I'll just have to wait a second. Okay. Okay, so we are live now on YouTube, and I'm going to start. We are live now on YouTube. So it's a pleasure to welcome Professor Sarbani Basu from Yale, sitting probably at her home to give this Wednesday colloquium. And I welcome all of you. I'm Jyotishman Dasgupta, the coordinator, the Wednesday colloquium coordinator. And I welcome all of you who are following us on YouTube live, as well as those who have joined in-house at TIFR for this particular session of the Wednesday colloquium. Before I hand over to my senior colleague, Professor Antia, to introduce Professor Basu, I would like to just mention that the Wednesday colloquium is the oldest forum for any science discussion in the Institute. Every Wednesday at 4 p.m., all the scientists gather, physicists, chemists, biologists, they all gather, faculty and students, and listen to a wonderful exposition of science that's going on all across the world. And this particular session is no different. We have a leading expert with us, Professor Sarbani Basu from Yale, who is going to talk to us about learning physics through astronomy, the sun and the stars as laboratories. I would like to thank Shravan for suggesting this name, and thanks for bringing one of our alumni back to TIFR for this colloquium. I'll hand over to Professor Antia to do the honors. Professor Antia.
Yeah, so it is a pleasure to welcome and introduce Professor Sarbani Basu. So, as has already been said, she actually joined TIFR Pune University MSc program in 1986. And after 2 years, she joined TIFR for doing the PhD. She completed PhD in galactic chemical evolution. And after that, in January 93, there was a winter school in helioseismology, which was being organized at the Physical Research Laboratory, Ahmedabad, and she opted to attend that. And since then, she has been working on helioseismology, and more recently, she has switched to astroseismology also. Now, she has done the postdoctoral fellowships at Queen Mary University of London, Aarhus University, and Institute of Advanced Studies in Princeton before joining Yale in 2000. And currently she is the chair of the Department of Astronomy there. And of course, she has done a lot of work in this. She will tell us something about that, and I'm not going to describe that now. So she has also won a number of awards. And 96, she was awarded the Venu Bapu Gold Medal by the Astronomical Society of India. Then in 2018, she has got the Hale Prize in Solar Physics from the American Astronomical Society. And she is also a fellow of the American Association for Advancement of Science. And she is also in the inaugural batch of 100 fellows of the American Astronomical Society. And she also is the deputy chair of the board of directors of Association of University for Research in Astronomy, of course, in US. So with this, I will now request Sarbani to start her talk.
Thank you very much for the kind introduction. And I suppose one of the silver linings of the current pandemic situation is that we are experimenting with the remote colloquia. Otherwise, this wouldn't have been possible at all, I suppose. So what I would like to talk to you about today is a bit of a reversal. Normally, we use physics to study astronomical objects. And instead, what I would like to give you a few examples where the sun and stars have been used to try and figure out some physics issues, properties of matter, and some fun stuff like is the gravitational constant changing with time? So the question is, how on earth would we do that? So stars are opaque. We can't really see inside a star, okay? And in fact, so much so that Arthur Eddington, who probably wrote the first ever textbook on stars, in that book said, our telescopes may probe farther and farther into space, but what can probe inside a star? So what you see in the background here is just a flyby through the Hubble Deep Field and the Hubble Ultra Deep Field. So we can study the depths of the cosmos, but what can we do about stars? So what is the appliance that can pierce through the outer layers? And that turns out to be seismology. The sun and the vast majority of stars oscillate all the time. The frequencies of oscillation depend on the structure of a star. And so the simple way to study physics is to vary the physics of the models of, say, the sun, because we know the sun very well, and see if the pulsation frequencies match. This is in a nutshell. This is not what we do, but you could think of this as what we do. Now, what about pulsating stars? This diagram is a key diagram in astrophysics. It's known as the Hertzsprung-Russell diagram after Einar Hertzsprung and Henry Norris Russell, who sort of came across this, discovered this quite independently. On the x-axis is the temperature of a star. It's a backward direction, and that's to do with how temperatures temperatures of stars used to be measured. So that's high temperature, that is low temperature. That is the luminosity of a star, so the energy output per second. And all these shaded regions are where we see pulsating stars. I'm going to basically be concentrating on this small region because this is where the sun is. Stars, like the sun, pulsate in many different modes, but the amplitudes are small generally. And but if you're patient enough, you can see many, many, many tones and overtones of the pulsation. Okay.
Can I ask a quick question, completely out of field? Could you explain what this pulsating phenomena is? What does that mean in the?
Oh, these are just the normal modes. The star oscillates. You have.
So it's just a physical normal mode of the object.
It's a physical normal mode, exactly.
Got it. Now I understand.
So yes. So for geoseismology, what happens is you have an earthquake and different ground stations look at. Get the signal, and then they figure out what's going on inside the Earth. Helio and astroseismology, we just use normal modes. It turns out that these days, even the geoseismologists are beginning to use normal modes of the Earth to actually study the structure of the Earth, but it's a very noisy because of everything else that's going on. So that's not quite done. It's much easier to do it in other stars. Okay.
Got it.
So as I said, we model a star, we can change the physics and then figure out whether the pulsations match or not. So since this is a physics audience mainly, a quick word on how we model stars, because this is, after all, the first step. For most stars, well, for many stars, a vast majority, we can assume them to be quite spherical. So for the sun, for example, the difference between the polar and the equatorial radius is, I think current estimates are maybe a few parts in 10 to the 5 or even less. So it's spherical. So we assume stars to be spheres, which means we can reduce a 3D problem to a 1D problem. We assume it's not just spherical, but it's also spherically symmetric. So a 3D problem is just a set of 1D equations in radius. And a star basically is a ball of gas. So all we solve for is conservation of mass, conservation of momentum, thermal equilibrium. We need to figure out transport of energy. And in normal stars, energy is transported through either by radiation, in which case we need to know how opaque the material is. So we need opacities, or by convection. Now, convection is a bit of an issue because convection is a 3D phenomenon. So we have to use approximations to model convection. And unfortunately, the approximation means that it introduces a free parameter, which can harm, but can also help. We need nuclear reaction rates. We need to figure out how the abundances of different elements change inside a star. For example, in the core, hydrogen is being converted to helium. So that's a change of abundance. Hydrogen and helium are settling down under, sorry, not hydrogen, but helium and all of the heavy elements are settling down under gravity. So that changes abundances. And of course, we need to know the equation of state, because that's the basic property of matter. If we change abundances at a given temperature, how would pressure and density change, or in any other way? To a large extent, you could approximate stars as being made of ideal gases, but that's not completely correct. And one of the things I'll talk about is how to do the equation of state, okay? So, okay. Now, I'm going to concentrate a lot on the sun because we have lots of data for the sun. It's close by, so we have independent measurements of the mass and radius and also luminosity. So modeling a sun, we have a number of constraints. We know the age of the sun, it's 4.57 gigayears. We know what the current luminosity of the sun is. We know the current radius of the sun. Now, the equations have two free parameters to play with. One is this parameter we call the mixing length parameter, which comes because we have to make approximations for convective heat transport. And the other is the initial helium abundance of the sun. Okay, we can't measure helium directly from spectroscopy because the surface of the sun is too cold to do anything. Okay. So what we do is we iterate over the initial helium, why not, and the mixing length parameter till we get a model which has one solar mass, but also one solar luminosity and one solar radius at the correct age. Of course, we also need to ensure that the metallicity of the star, that is, Z is the mass fraction of heavy elements. So for astrophysicists, there are only 3 different elements that normally exist. There's hydrogen, mass fraction is given by X, helium, mass fraction is given by Y, and everything else is a metal, and the mass fraction is given by Z. So normally you measure Z over X, so you have to also get that right, and then you get a model of the sun. Okay.
What, Sarbani, sorry, what else is known about the elements? In the sense, everything else.
We do know the abundance of many other elements, but the surface abundance, of course, okay, because that's all. But in terms of modeling, yes, you could use each individual element, but that doesn't make too much of a difference to the internal structure.
Okay. Okay.
It's a second order effect. The first order effect is simply Z. So let me step back to give you a schematic diagram of the sun to say what physics affects which part. So this is, think of it as a cutout. This zone between these 2 radial lines is where energy is transported by convection. So what matters here is mainly the equation of state, because convection zone is basically isentropic, and the entropy, of course, is determined by the equation of state. Where where exactly the boundary between the radiative zone and the convection zone lies depends on metallicity and opacities. Opacities are basically, you could think of as for a given, say, unit heavy element abundance, how opaque would the matter be? So that I would call that intrinsic opacities, because opacities determine where this boundary is. And that is simple because remember that every material has a maximum temperature gradient that it can have before it becomes unstable. So that determines where this boundary is. And with helioseismology, we know the position of this boundary very, very well. It's at 0.713 plus or minus 0.001 solar radius. So it's a big constraint. The radiative zone depends on the opacities. And of course, opacities for a given intrinsic opacities, that'll depend on metallicity. And of course, equation of state also matters. In the interior, equation of state, of course, plays a role in the very core, and also what matters are the nuclear reaction rates or any energy transport, any energy loss or energy gain that can happen here. So this is where these different bits of physics come in. Before I go further, I want to give you a crash course in seismology, okay? So the sun oscillates and pulsates in millions of different modes, most of which we can't even measure. The usefulness of the sun and sun-like stars in seismology is that the oscillations are linear and adiabatic. Classical pulsators are very difficult to deal with because they're nonlinear oscillations. Now, all the observed modes of the sun are basically acoustic modes, so sound waves, sound modes. We call them P modes, P for pressure, because the restoring force is pressure. And for the sun, not for other stars though, because we can't see surfaces of other stars, we also see surface modes known as F modes. Now, each mode is characterized by three numbers. There's the radial order n, which is, think of a pulsation, okay? It's pulsating, it's a three-dimensional pulsation on the surface as well as inside. The number of nodes inside is the radial order. L is the number of nodes on the circumference because the surface is basically described as spherical harmonics. And all of us in our quantum mechanics classes have had to work through the hydrogen atom wave function. And so we know what spherical harmonics are. So L is the number of nodes along the circumference. And M, the azimuthal order that goes from plus L to minus L, is the number of nodes on the equator. Okay. I won't be talking about M's much. It's the L and the N which really matter.
Can I ask a question? Actually, it's not my question. Ambarish, could you unmute yourself?
Yes, hello, can you hear me?
Yes, please go ahead.
Yeah, I wanted to ask if the values of Y, the helium abundance, and Z, the metal abundance, independent of each other for a given star?
That is $1 million question. Because Y cannot be measured in astrophysics, thus far at least, most people assume that Y and Z follow in lockstep, because as the universe evolves, both helium and metals, the amount of metals increase. And it's often assumed that they increase linearly. However, with astroseismology, we can get an independent measurement of Y. And so we assume that they're not, that they can be measured independently. The jury is still out how well we can do that and what the Y versus Z relation is. But for the case of the sun, Z is measured, Y in the surface has been measured, but even the initial helium abundance comes through solving the equations, because without keeping that as a free parameter, we cannot get a model of the sun. So we know in that sense what the initial helium abundance of the sun was. Yeah. Okay, so to come back to seismology, so the surface is spherical harmonics. So we have L's, which is the number of nodes on the circumference, and M, which is the number of nodes on the equator. Now, I don't like to give equations in a talk, but just if so you wonder, in the simplest form, the oscillation equation is this. It's a simple looking equation, but that's because some fairly hairy assumptions have gone into it. But there are two characteristic frequencies. There's the Lamb frequency. C here is the speed of sound, not light. And the buoyancy frequency. And the nature of the modes depend on these two. So modes with frequencies higher than the Lamb frequency and the buoyancy frequency are what's called P modes. Modes with frequencies lower than the Lamb frequency and the buoyancy frequency are G modes, G for gravity, because the restoring force for them is buoyancy, not to be confused with gravitational waves, completely different thing. Okay. And for the sun, we only see P modes, and for a given L, P modes penetrate as deep inside a star as it can till it hits the Lamb frequency. So these dashes are Lamb frequency of degree 1, 5, 20, and 100. So this is the radius. This is a solar model. This is the radius. This is frequency. This solid line is the buoyancy frequency. The dashed lines are the Lamb frequency with the degree written. So any mode will travel to a distance of a given degree, will travel to a distance given by where it hits the Lamb frequency. So you can see that a mode of this same frequency will travel deeper inside a star for L of 1 than it does for L of 5 or L of 20 or L of 100. So that's basically how you can build up a picture of this of the sun.
I have a quick question on the previous slide.
Mhm.
The G modes are never observed. Is that something?
That is because the buoyancy frequency is imaginary in a convection zone.
Oh, okay.
The sun has a very extensive outer convection zone. G modes have been observed in white dwarfs, and they have also been observed in higher mass stars, like 2 solar mass and even higher, but not for the sun, not for the lack of trying. People have been trying to observe G modes for a very, very long time. So if the sun were spherically symmetric and not rotating at all modes with the same L and N, but no matter what the M was, would have the same frequency. Think of it again in terms of your hydrogen atom energy level. It's degenerate, 2L plus 1 times degenerate, unless you apply something, in the case of hydrogen atom, electric field or a magnetic field when the modes split. In this case, anything that breaks spherical symmetry will make the modes split. In the case of the sun, it's rotation. So the modes split. Now, because we can observe so many modes in the sun, what we do is we write the frequency of any given NLM as a part of a frequency that depends only on N and L and an expansion in M. This reduces the noise in the data to try and fit. But the nice part about this expansion is you can show that the new NL depends only on the structure, and the odd order components of this expansion depend only on rotation. So you can actually determine both structure and rotation of the sun this way. We are going to talk only about new NL. And as was clear with that slide with the equation, different modes penetrate to different depths. And that's why we can actually build up a picture of this of the sun and use that to do our work. So what does solar data look like? This is a one-year data set from two different instruments. On the x-axis is the spherical harmonic degree L. Please remember that low degree modes penetrate deep inside a star. High degree modes are shallower. Y-axis is the frequency. This ridge structure is basically the observed ridge structure was convinced people that first in the early 1970s that these oscillations are indeed normal modes and not just atmospheric oscillation. This happens to be the surface mode. This is the mode with one node inside, two nodes inside, 3, 4, 5. The different colors are for a very interesting, for a different reason. These red ones are the really low degree modes of the sun. So they are global modes in the sense that they encompass most of the sun. So L of 0, 1, 2, and 3. For other stars, that's all we can really observe, which is why I've plotted them in a different color. The cyan bit is what we normally use for most of helioseismology. The blue bits, the errors in the data are still very large because of the nature of the modes, and we're still trying to figure out how to use them. So most of all the results that I'll show will be with the red and the cyan bits. So if I zoom in, this is what one data set looks like, L and NIR. And why this works is this. These are 1000 sigma error bars. The data are extremely precise, and this is what we exploit. Okay, so how do we use helioseismic data? So in most of astrophysics, what you do
sorry,
yeah.
I know it's the fun part for you, but just wanted to go back. How did you observe these modes now? In what kind of...
So these are Doppler measurements. So what you do is take a Doppler image of the sun.
Okay.
You take an image every minute.
Okay.
Well, these days, the space-based one does every 45 seconds, but that's okay. This is an older space-based one, which took a 1K by 1K image every minute.
Okay.
What you'd first do is remove rotation, because the biggest signal is the 2 kilometers per second rotation. Then you do a spherical harmonic transform to get different L's for each observation. You get a time series of the spherical harmonic transforms, do a Fourier transform, and that'll give you the frequencies.
Very interesting. Okay.
So, yes, there are many other nitty-gritty involved, but that's it in a nutshell.
Okay.
Okay. So what do we do? In astronomy, generally, you take an observation, you make a model of the observation, calculate the observables. If the observables agree, then you have a good model, and the model is a proxy for your object. Comparing frequencies for the sun doesn't quite work very well. What I'm showing here is the frequency difference between a really good model of the sun, frequency difference between the sun and a really good model of the sun. And you can see there's clearly a systematic difference. Some of this difference is because of the fact that modes which are very shallow are easy to perturb than modes that go deep inside. That can actually be corrected for. If we correct for that, you still get this very systematic, frequency-dependent difference between the frequencies of the sun and the model. We know now, and we've known that for a very long time, that this difference doesn't arise from differences in the internal structure of our model compared to the sun, but arise from problems in modeling very close to the surface, like convection or modeling the atmosphere of the sun. Okay. So the same interior physics could give rise to, this is known as the surface term. So this frequency dependent term is known as the surface term. And it turns out the same interior physics could still give rise to different surface terms. So this is the frequency difference between two models where the atmospheres are different. So this is the difference in the sound speed between the two models. So you can see it's flat inside. This is the frequency difference if I change how I model convection slightly. So, and we can't really get rid of this. We don't yet know how to get rid of this because part of in the real case, there's convection, there's atmosphere. There's also the fact that the modes, the adiabaticity of modes, which I talked about, that they're linear and adiabatic, it sort of breaks down very close to the surface. Turns out any perturbation close to the surface will give rise to a frequency difference, which is almost zero at low frequencies and increases with high frequencies. So what do? This sort of stops us from doing much, right? Turns out we have enough data. So instead of trying to model, find its frequency and compare, we can invert the frequencies to figure out what the structure is. The frequency, the oscillation equations that was shown by Chandrasekhar in 1964 form a Hermitian linear value, eigenvalue problem, which means we can use the variational principle. That's the equation. Okay, omega is the frequency, can be observed. C is what we want to find, sound speed. Rho is density, which is also what we want to do. G is acceleration due to gravity, which we can find in terms of density. P is pressure, which we can find through hydrostatic equilibrium from density. So this is basically an equation in sound speed, density, the frequency, and the eigenfunction, the displacement eigenfunction. We can observe the frequency. We want to find out sound speed and density. Problem is, we don't know what the eigenfunctions are. So this is where we apply the variational principle and linearize this equation around a known solar model. And if you recall your variational principle from your days of quantum mechanics, to the first order, the eigenfunctions can be the eigenfunctions of the ground state, in this case, the model. So once we linearize it, we get an equation in the relative difference between the frequencies of the sun and the model, a known function, these are the kernels, a relative difference in the squared sound speed, and the relative difference of a density. The two kernels are, of course, different, but they're known. We can calculate them. And because there's the surface term sitting there, we have to add a function of frequency to take into account the surface term. Does this work? Indeed, it does. Otherwise, I wouldn't be talking to you. These are inversions between two models. The black line underneath is the exact solution of the relative difference in the squared sound speed and the relative difference in density. The points are the inversion results. So we can go quite deep in. We don't have enough information much deeper inside the core. For that, we use frequency combinations that are actually sensitive to those cores. And that frequency combination is usually called D02. So this is the difference between L of 0 and L of 2 modes of adjacent degree. And the reason it's a bit more sensitive to the real deeper regions is, I'll try to explain this figure. So this is radius, the x-axis. That's the kernel that I talked about, the kernel for the inversion. So these lighter gray lines, I've actually plotted two kernels, one for L of 0 and one for L of 2, okay? One different in n because that's the formula. And the deeper black line is the kernel for the difference, the small difference D02 here. And you can see that all the outside sensitivity becomes almost zero, and you're left with a somewhat more sensitivity in the core. So which is why parts where we cannot really invert, we use this. Okay, so what have we learned? Just to show that our models, solar models, are actually fantastic, these are the sound speed and density, relative sound speed, squared sound speed and density differences between the sun and two solar models. Look at the scale. It's 0.7% at the maximum. Any other field in astronomy, we would say, oh, we've got an exact match. Except here, you can see that these are the real error bars. So this is a highly significant difference. So yes, our models are very, very good, but yes, there are problems. The problem here is, we believe, is related to the fact that there is a shear layer. This is the convection zone, and that's the radiative zone. The convection zone of the sun rotates differentially. The radiative zone is a solid body rotation. So the interface of these two rotations produces shear, and we believe that is what sort of washes out a big difference inside the sun, which doesn't happen in our models. But I would just like you to see, particularly in the core, how small the differences are. Incidentally, the difference between two models is what opacity has been used. So there are two main opacity tables that are used by the community. One is the OP opacities, the other the opal opacities, and one of these has, the blue has opal, the red has OP. Okay, so just to give you an example of how we constrain the physical processes that go on inside the sun, till before the early 90s, even though everybody knew that under gravity, heavier elements should sink down with respect to hydrogen, the process was thought to be so inefficient that nobody bothered to model it. But the sun is 4.5 billion years old. That's enough time, even for an inefficient process. If you do not include that process, the difference in structure between the sun and that model is given by this blue line. If you include the process, it's the red model. That's the difference in density, that's the difference in sound speed. And you can see that immediately, yes, you have to include that process, otherwise your models are going to be very wrong. There are other issues with not including the process. For one, if you do not include that, the surface helium abundance of the sun would be the same as the helium abundance it was born with. And yet detailed helioseismic observations of the surface helium abundance tells us that it's much lower. The red model actually fits the surface helium abundance measurements also. So that's one way you can use helioseismic data to figure out what's going on inside the sun. Make a model, and look at the differences. Do you really need that process or not? So let's get to fun stuff. Physics. And I'd like to start with a now solved problem, which was the solar neutrino problem. Now, to talk about, so this figure just shows you the spectrum, energy spectrum of different types of solar neutrinos. So you have the PP neutrinos here, the beryllium-7, the BEP, which is, you can see that the flux is quite small, the beryllium, the boron one here, this is the 7 beryllium. Now, in the 1960s, that's when I think technology was good enough, when people decided, particularly Ray Davis, John Bickel, that we had hitherto assumed that stars shine by nuclear reactions. That was the only way you could. But was there any proof? And the big proof would be nuclear reactions would produce neutrinos. If you could see neutrinos from the sun, that means nuclear reactions would do occur. So the first experiment was the chlorine experiment under the home state mines in the US, and then followed by a few in Japan and elsewhere. So yes, they measured neutrinos. So yes, indeed, nuclear reactions occur in the sun. However, the measured neutrinos for the different experiments, and that's given in blue, was much less than the predicted neutrinos, which are these other colored bars. So this is chlorine. This is what would be expected. This was what was observed. This is water. So these are the Kamiokande and Super Kamiokande ones. Again, expected, predicted. These are the gallium experiments. And this was a heavy water one. Okay. So yes, they're neutrinos, but they're not enough. So for nearly 30 years, people believed the problem lay with the solar model, that the solar model was deficient in some way, because after all, solar models need a lot of different inputs to make, like you have opacities and nuclear reaction rates and all the assumptions that go into convection. So people spent a lot of effort in making non-standard models of the sun. However, we've seen that for standard models of the sun, the science speed difference, which translates to temperature difference in the core, is nothing. But we knew that only after we had enough helioseismic data to actually see this difference. If I made a non-standard solar model so that I would say get the beryllium neutrino fluxes to match with observations, this difference in the core would be right up here at the 10% level and not at the fractions of a percent level. So helioseismologists at that point basically said that no, the solar neutrino problem does not lie with the sun. It has to be with particle physics. And till that point, even though people had talked about possible massive neutrinos and flavor mixing between neutrinos, that was not the consensus view. So helioseismology showed that that had to happen. But of course, particle physicists like to do their own thing. So they built a heavy water detector in Canada, the Sudbury Neutrino Observatory, which observes both the electron type and the mu type neutrino. And when it did the observations, turns out that the observations and the predictions match almost embarrassingly well. And that is one of the few problems in astrophysics that was solved exactly, so much so that we don't even talk about this anymore. But that is one way where we had shown that the problem is not with astrophysics. It had to be the standard model of particle physics. Okay, what about the physics of stellar interiors, like the equation of state? Now, there are two common types of equation of state. One is built on the so-called chemical picture of plasma. Atoms and ions and particle interactions are treated as chemical reaction, and the equation of state is derived by, you write the total free energy and use that. The other is a physical picture, which sort of describes plasma in terms of the fundamental constituents. Now, for astrophysicists, we don't calculate this. Others calculate equations of state for us, and we just use them. And the equations of state based on the chemical picture, the old one is the so-called Eggleton, Faulkner, and Flannery equation of state. It was basically the Saha equation for ionization, with a prescription to induce pressure ionization at high densities, because the Saha equation does not include pressure ionization. And bound systems are always assumed to be in the ground state, and heavy elements are assumed to be fully ionized, which is not completely correct. This, however, did not include corrections to pressure due to Coulomb screening. So that was corrected to make the Coulomb corrected equation, EFF equation of state. These were sort of quite simplistic in some ways. So then came the MHD equation of state, which was much more sophisticated. And I should point out, MHD here is not magnetohydrodynamics, but Mihalas, Hammer, and Apen, the three authors. So these were based on the chemical picture, and the physical picture is opal, which describes plasma in terms of its fundamental constituents. So the question is, which of these is better? So what do? You make solar models, compare. Frequency differences, as said, don't tell us much, except in the EFF case. If you recall, you may recall that the surface issues affect only high frequency modes and not low frequency modes. In the EFF, however, the frequency differences are all over the place. This just shows that the model is terrible. So EFF equation of state gives horrible models. Just looking at frequency differences, the CEFF, MHD, and opal, you can't really make too much of a difference. But we can look at more detailed stuff. So for example, if I find the solar sound speed through inversions and calculate this quantity, which is a dimensionless sound speed gradient, it'll look like this. This is the convection zone. This peak you see here is the second helium ionization zone. And the shape of the ionization zone depends on the equation of state. So that is the observation. This is from a very old paper, so we have slightly better things now. These are what happens if you use the EFF equation of state. So clearly there's a mismatch. Opal, and so black is observation. Red and blue are opal with two different helium abundances. And the brown and green are MHD, again, two different helium abundances. We can't use this to say too much, except in both cases, the shapes are slightly different. So we need to actually do a proper inversion instead of looking at these. When we do that, we don't test sound speed, we test the adiabatic index gamma 1. So gamma 1 for ideal gases, you can simply think of it as 5/3. That's Cp over Cv. We are dealing with non-ideal situations like ionization, so it's less than 5/3. That is the second helium ionization zone. The different colors are models with different equations of state. So we have EFF, CEFF, opal, and MHD sort of merged together. However, if we do the inversion to find the differences with respect to the sun, we can again see that EFF is really bad. Opal is better than MHD, except perhaps very close to the surface. So this is the relative difference in gamma 1. So you can see EFF bad, opal, MHD same, very deep inside. But in the intermediate range here, opal is better than MHD, closer to the surface, MHD looks better. We can actually do a better job there, and MHD is indeed better than opal, very close to the surface. And turns out when we looked into it very deeply, it's to do with how the ionized hydrogen atom is treated. So you can actually go back and look at the causes for the differences. A more interesting case, I would think, was the difference in gamma 1, the adiabatic index in the solar core. In the solar core, everybody expected gamma 1 to be 5/3. And yet, when people looked, this was by, it was oh, sorry, this should be Elliot, not Elliot. It was Julian Elliott's thesis. When he looked at the frequency, the gamma-1 difference between a model made with the MHD equation of state and the sun, and even the opal equation of state and the sun, instead of getting 0, they got this difference. And there was no difference between opal and MHD in this. Turns out both sets of authors had assumed that at temperatures at the solar core, the electrons were going to remain non-relativistic. Now, gamma-1 is 5/3 for a non-relativistic ideal gas. If you have a relativistic tail, it'll decrease. If you remember, for pure photon gas, gamma-1 would be 4/3. So given that the electrons have a non-relativistic tail, gamma-1 in the sun is lower than that in the models. Both equations of state have since been corrected for this. Okay. I don't have too much time left, so I'd like to go into some fun stuff. Can we constrain the value of the gravitational constant? Because if you look at this value, okay, the errors come in the 4th decimal place. So you would think maybe we have data that are they're really precise. Maybe we can do something about it. Turns out we may not know G very well, but we know G times M sun very well. We know that to 12 decimal places. And in the early days of helioseismology, I remember getting papers from particle physicists who tried to constrain G using seismology, quite forgetting that GM sun is known to 12 decimal places, because now we know if you want to try a non-standard G, you'll have to make a small change in M sun so that this remains the same. Can you do anything? Well, this was a set of inversions with models with slightly different versions of G, but keeping GM sun the same. And even the authors say that they're not willing to, maybe one of them would be better than the other. But what you don't see underlying is the standard model, which actually falls under the gray curve here. So they can't really do anything. So too bad. We really can't. What about the evolution of G? Because there have been some theories which suggest that G can be time dependent. So in the solar model, a sun is 4.5 billion years old. Maybe it's good enough to see the time dependence of G. After all, GM sun is constrained only today, not when the sun was born. If they do that, so this was the first attempt before inversions became too popular or not everybody knew how to do inversions, and they just looked at the frequency differences that were sensitive to the core. And yeah, they've just put limits on how G would vary. There have been some, actually, this was revived just last year, and there were a couple of attempts. This was with better data done earlier this year, because now the data are so much better. Even the helioseismic data are so much better. And again, all you can do is put an upper limit. And it's a tiny, tiny upper limit, 10 to the minus 13 per year. You can actually do that with other stars too, because your value of G will change how a star evolves and on the HR diagram. I won't go into the details, but again, what seismology is telling us that the limits, the time variation of G has to be very, very small. I'm going to end with something where the physics is a bit beyond my comfort zone, but the astrophysics is not, so I'll try that. One of the non-standard physics people have tried out is assume what happens if axions are produced inside the core of the sun. If they do, they will couple with photons. So they're formed through photons, which means you're losing photons, which means you're losing energy. And the energy loss can actually be calculated. Depends on the temperature and the density, which we can know from our models, and a coupling constant. So the question is, do we know what the coupling constant is? Can we put a limit on it? So people made models, did the inversion, and you can see two sets of models. They have different heavy element abundances because there's a bit of a dispute about what the heavy element abundance of the sun really is. So they tried to use both. And you can see different values of the coupling constant between the axions and photons change the core structure in a slightly different manner. Okay. But you can already see that the axion coupling can't be very large because the difference is smallest for no coupling. This is a sort of, there's not much quantitative information from this graph, but for the models, you can actually calculate things like the neutrino fluxes, the surface helium abundance, the position of the base of the convection zone, and look at all of those as a function of your coupling constant. So that's the coupling constant. The red and the blue are the two flavors of solar models because of the dispute of heavy elements. This is the surface helium. The horizontal line is the observed surface helium. This is the boron neutrino flux. The horizontal line is the observed flux. This is the beryllium flux. Again, horizontal line is the beryllium flux. And if I forget about these two, because metallicity plays a role there, this plays a lesser role, you can see that if there is indeed axion production by the photons interacting with the heavy elements inside the core, the coupling has to be really small. Otherwise, we would have seen the effects in the neutrino productions. So, parting thoughts. Helioseismology has allowed us to study the sun in exquisite detail. I mean, I haven't even talked about solar dynamics because that really doesn't tell us too much about fundamental physics, but we know that too. So the structure of the sun, knowing the structure of the sun allows us to test inputs to solar models, and that's why we can use the sun as a laboratory. So for example, what we've done is which equation of state we should be using, or rather which we should not be using. And although I haven't shown it and I skipped that, the data have even allowed to put limits on nuclear reaction rates. And for those of you who are not cognizant of nuclear reactions in stars, nuclear reactions in stars take place under very low energy conditions. The Boltzmann factor is e to the minus 1,000. So nuclear reactions take place through through tunneling. Nuclear reactions that are measured are through, say, nuclear reactors and accelerators have to be measured at high energy conditions. So people do the measurements, use the theory to extrapolate at low frequencies. So there's always an uncertainty in the nuclear reactions. And as people are getting better and better and better at measuring nuclear reactions at low frequencies, the reaction rates keep changing, in some cases, some key reaction rates. But helioseismology does allow you to put some limits on nuclear reaction rates. So was the term. And yes, we've been trying to test some fundamental parameters like axions. People have also been trying to test things like hidden photons, and I talked about the variation of G. I would consider that the real fun part of helioseismology. So not just trying to figure out what the sun is like, but what else can we use the sun for? So thank you very much for your attention.
Thank you, Professor Basu. This was very nice talk. Of course, I had a connection from a chemistry point of view to the normal modes idea of objects. So yeah, thanks for that connection. I will now let people from the audience ask questions. Are there any questions? Please raise your hands. You can raise electronically or basically come with an unmuted audio. Indranil? Indranil? Yes.
No, I didn't raise hand.
Okay. Somebody whose screen name is Moto G55S Plus. I don't know.
Why did you?
Yeah. Sorry. I have not changed the name. It's Vivek Datar.
Vivek. Okay. Yes.
Yeah. Okay. So my question is the following. Very nice talk. You mentioned something about the limits on the axion photon coupling. Now, there have also been attempts to try to measure these axions through their interactions with the magnetic field on the Earth at CERN, for instance. So where you convert an axion to a photon and then look for that low energy photon. Now, are these limits better than those limits, or it's difficult to make a connection between the two?
I actually do not know the answer to the question. I haven't really been following this much, except I think we should be able to compare as long as yeah.
It may be model dependent, perhaps, the coupling to the mass and so on, but yeah, maybe they should be.
No, the model dependence comes in one of the approximations. So if I go back to, so this function here, that apparently for solar conditions can be approximated to this here. That is where I think the model dependence would come in. Otherwise, I don't see an explicit model dependence because we are testing it against the sun.
No, I'm saying that there is also a model dependence from the particle physics side.
Yes, of course, but that is that would be and that's where this is the particle physics model that is basically used.
Yeah.
So see a question by Alakre about astroseismology of massive stars. It is being attempted, it is being done. Beta Cepheids are in fact one of the big targets of, there's a whole group in Northern Europe looking at Beta Cepheids. I am not aware of anything yet about rotation rate through seismology. They're looking at the light curves, etc. But I don't think they've measured rotational splittings. They have measured rotational splittings of slightly lower mass stars, but not of Beta Cepheids in particular. So yes, rotational splittings have been measured for, I think 3 and 4, some 2.5 to 3 solar mass stars. And I would refer you to papers by Connie Artz's group. I'll write the name in the chat box. Group has been looking at high mass stars and how to get rotation, etc., from high mass stars, because the seismology, the seismic analysis is slightly different. So Connie has a paper, a review out in Reviews of Modern Physics, I believe. I don't think it is quite published, but it's definitely on archive. So there's a review which talks about how to look at the rotation, internal rotation, etc., of highish mass stars. So I would refer you to Connie.
Okay, Alok says thank you. Are there any other questions? Okay, Bhashwati.
Yeah, I just, Sarbani, this is more of a general question. helioseismology has done a fantastic job. So in your opinion, where is, say, solar study of solar physics headed? Like, what are the next big problems which the solar physicists are looking into?
They are all, the big solar physics problem now is what had been big for a long time, which is magnetic field generation, the interaction of solar magnetic fields with the heliosphere, and particularly the interaction of solar magnetic fields with the Earth's magnetosphere. Because there is really no way yet to actually predict solar storms and particularly solar mass ejections. So in 1858 or 59 was the so-called Carrington solar flare. And it really harmed what the then highest technology was, which was the telegraph wires. It has been calculated that if a Carrington event took place today, the damage would be enormous. And I'm not talking merely in terms of a monetary amount that's been sort of calculated as trillions and trillions of dollars, but just basic infrastructure like the power grid being off, and the power grid being off because transformers burning out. And the problem is, with so many transformers burning out, to replace them would take weeks. So it's a question of the economy completely shutting down for weeks or months. So some recent colleague told me that the pandemic would seem like a good thing at that point. But the problem is we cannot yet predict events like that because we really don't know the details of what causes these eruptions. So the biggest issue in solar physics now is trying to look and understand the magnetic recombination effects that might give to these eruptions, whether there are precursors, say subsurface precursors that we can look at, which is where helioseismology might come in. Not the sort of helioseismology I talked to you about, but more the sort of shallower layer helioseismology, the sort of thing Shravan sometimes does. But that is the biggest issue in solar physics right now. It's one of the reasons, since I don't really have a training in plasma physics, which is why I moved to do astroseismology, where we do statistical studies of stars like the sun. And so if data from Kepler on stars like the sun is to be believed, superflares like the Carrington event are actually quite common, which is worrying. But that's just a statistical study counting numbers. So that is the biggest problem.
Okay. Shravan wants a question. Yeah, Shravan, please, can you put your video?
Yeah. Hi. Hi, Sarbani. Sorry, I was
Hi.
off with you. Thanks again for this lovely talk. I just wanted to ask you in terms of, I mean, of course, we get to speak to each other after this, but, for the benefit of the audience and so on, since you've been working and at the forefront of all these exciting astroseismic projects, what are your broad thoughts on astroseismology? Where is it headed? And what do you think are the most exciting things we'll see in the coming years?
That's a very broad question. So I would say the answer goes in two directions. One is the use of stars as tools to study the chemodynamical evolution of the galaxy and even the local group of galaxies. For that, what we need are ages of stars, and seismic observations can give us masses of stars, which in a model-dependent manner, we can give ages. That, I would say, to me, is the less interesting part. Yes, that keeps me in funding, but it's not really basic. I mean, we know how to do that, so we do that. It's pretty routine. The more interesting issue is the more details of what happens inside stars. So one of the things we know is that we are not able to model the power spectra of red giants. The red giants have modes which are so-called mixed modes. They are G mode-like in the core and P mode-like at the surface. And they are highly dependent on details of things like the profile of the buoyancy frequency. And it turns out that core helium burning red giants, we can't really explain the mixed modes at all. So there are processes that are going on in stars that we don't understand, which connects to the fact, which is perhaps the more fundamental issue, is we know how now, thanks to statistically speaking, how the internal rotation rate of a star changes. So the simple picture is that as a star evolves, its core contracts, so conservation of angular momentum would speed it up compared to the surface. Yes, we see a speeded up surface, but the speed up is much, much, much lower than what would be expected from a simple conservation of angular momentum. In other words, there are processes that transport angular momentum from the core to the outer envelope. So much so that if you look at an ensemble of red giants, as the stars go up the red giant branch, in fact, so as a star goes up the red giant branch, its core gets smaller and smaller and smaller. So you would expect the core to spin up as it goes up the red giant branch. Instead, many of them show signs of spinning down. So in that sense, I would say the more fundamental problem that is what astroseismologists need to look at is what are the angular momentum loss mechanisms in stars that cause the cores to spin down? So of course, they're the usual culprits, magnetic fields. That's a showstopper because once you say magnetic fields, everybody stops. But there could be things like internal gravity waves and meridional flows that we don't know about, strong meridional flows, which would transport angular momentum. And each of these, if they're strong enough, would leave its imprint on structure also, which would affect the mixed modes. So we need to get those mixed modes right.
Thank you.
Okay, so Vivek again has a question.
Yeah. Okay. The question is about these strong solar disturbances that might cause damage to both our communication systems as well as to the power distribution system.
Mm-hmm.
Now, what is the? I mean, aren't there already plans to put satellites in between the sun and the earth so that Lagrange point and so on, that would give us an early warning of such events?
Yeah, it gives you about a 45-minute to 30-minute warning.
Okay.
And
so at least you would be able to switch off things, perhaps?
Yeah, and we had done that in, I'm trying to remember, it was the Halloween flare. I think it was 2003, 2002. It worked, but it's still, there is no worldwide network yet for the information to flow. So the Halloween flare, which was a much, much more gentle flare compared with the Carrington event, yes, the satellites were turned off, actually turned away. And except for one Japanese TV satellite, everything worked fine. Airplanes had to be rerouted because you don't want to fly over the magnetic poles when such a event happens. The radiation damage to humans would be bad. So yes, you might prevent catastrophic damage, but it's a question of how prepared everybody is to quickly switch off their circuits, even if there's a mechanism to switch things off quickly and safely, because you might not get more than a 45-minute to 30-minute warning.
Yeah. But, such systems are probably in place if there are, for instance, tsunamis and so on. People get warnings on timescales of that order. So
Yeah, the tsunami warnings are actually a bit more sophisticated than warnings about this, surprisingly.
Yeah. Mhm.
So,
Okay, thank you.
Oh,
and also the other issue people are worried about this is astronauts. You can't really
Yeah.
bring back an astronaut from the International Space Station in 30 minutes time.
Yeah.
Or if because NASA started these studies because they were interested in sending people back to the moon or even to Mars.
Mm-hmm.
And how do we protect them?
Mm-hmm.
okay.
Okay.
Bhashwati?
Yeah. So actually, my question is sort of a continuation of Shravan's question, and I would like to take it a bit towards the observations. And I'd like to ask you that where do you think? So I understand the sort of problems which are in the burning issues in astroseismology, but do you think the currently available data or the data that you expect to come from tests is sufficient, or the observations still have to wait for Plato or some subsequent mission?
There is a lot of unexploited data from Kepler. TESS is not going to be good for this because TESS, except towards the ecliptic poles, the time series is only 27 days. It doesn't give you sufficient frequency resolution to look at this. Kepler, on the other hand, there's still thousands of stars which nobody has bothered to look at the data as yet. I mean, there were practical issues, but those are being solved now. I think we have to wait for Plato for long time series, though unfortunately, just like TESS, Plato, the pixel sizes are too large. So yes, you can observe a lot of stars, but again, Plato being an exoplanet mission, the targets will be sort of decided more by the exoplanet people than us. We are hoping that just like Kepler and TESS, at least red giants would be automatic byproducts. Like TESS, it's not looking at red giants, but because it's taking an image. It's taking an image of the sky every 30 minutes. We automatically find red giants there. And for red giants, an image every 30 minutes is more than enough. For the less evolved stars, 30 minutes is not good, though currently TESS has started its extended mission. So the full frame images are taken every 10 minutes. So that's actually lets us go well into the subgiant range. So that might be helpful, but this fact still remains is that 27-day time series is really not good enough. So Plato. About exoplanet people requiring small pixel sizes, Alec, that's what we would think, but they are more interested in the nearby bright stars. So those are far enough, they're spread out enough that the larger pixels work fine for them. Most of us, the astroseismologists, would love to do seismology of nearby clusters, but the clusters are crowded fields, and that's where things get a bit problematic.
Okay. Arya Nachiketa has an interesting question. Is there any collective mode of oscillation in the sun, like in the atomic nucleus?
I don't know the answer to that, I'm sorry, because I don't remember offhand what the collective modes are for an atomic nucleus. So I don't know if I can make the connection. Sorry about that.
Okay. Okay. Are there any other questions for Professor Basu? Well, if there are none, I would like to formally thank you again for this wonderful talk and joining us from at a very early morning for you over there. So joining us at that time and being patient and answering all the questions. I would request you to stay over You can take a break and we can you can rejoin in 10 minutes if you want. 5:30, that's the time for meeting with people. I'm going to just stop the